All right, so we're going to start doing some thermal physics now. And we're going to start by talking about the difference between microscopic and macroscopic. Okay, sorry, my pen wasn't working there. So we're starting thermal physics. So this is basically mixtures of some thermodynamics and some statistical mechanics type things. And we're going to start by discussing the difference between microscopic and macroscopic. So basically, microscopic is when you're looking down at the really small scale of things. Something you'd have to look at with a microscope. Something down micro, meaning 10 to the negative 6. That's that very small scale. It actually goes down smaller than that. We're talking down on the atomic scale a lot of times, down inside the atoms and things like that. That's microscopic scale. This would be the interaction between atoms and molecules and particles and stuff like that, between electrons and the nuclei and all that kind of thing. And then over here is macroscopic, where we're looking at the whole object. So if we had like a hunk of metal or something sitting here, the macroscopic view would be just to look at this hunk of metal as one big thing. The microscopic view would be to come in, take some tiny little section of it, blow it up. Oops, that wasn't very good. Blow it up real big and look at the actual like atoms and molecules and stuff that are in there making that substance up. So what we're about to do is a lot of work on microscopic ideas, but looking at a lot of it through macroscopic ideas, kind of averaging it all out, looking at the whole thing rather than each individual thing. So you'll learn what it is on the microscopic scale, and then we'll do macroscopic type calculations on it. Okay, and to start, let's talk about the different states of matter, what you have been taught, and what you have to know for this course is that there are 3 states of matter. 3 states. Okay, so this is what you need to know: solid, liquid, and gas. And so these are the 3 that you're supposed to know, the 3 states. And you may have heard other ones like Bose-Einstein condensation or plasma to make this a total of 5, and that's fine. We'll discuss them, and then I'll kind of give you the more modern view, more modern physics view on these things. It's not really what you need to know for this class, but it's interesting nonetheless to kind of keep in the back of your mind that this is not really what is thought of as states anymore. So solids, these are going to be when there's a certain arrangement of the atoms and molecules, and they stay in that arrangement. They may vibrate ever so slightly next to each other. They may move around a little bit, but they're not rearranging on their own. They're not changing and swapping positions around or anything like that, and it stays basically its same shape. There are some exceptions to this, the things that are kind of like amorphous solids, where you can, like gum or certain metals, where you can bend them and move them, and these atoms and molecules will rearrange if you apply pressure to them. They're not liquids, they're amorphous solids, but for the most part, when they're left to their own, the solids tends to just keep its shape, and the molecules and atoms and stuff that make it up don't rearrange themselves. The next kind is a liquid. A liquid, it would be something where you could have it in an open container like this, and so it'd be like water or something, and the particles are in here, and they can move around randomly and change positions and bump into each other, but it's pretty dense. There's a lot of them. They're pretty tightly packed. And then the last one is a gas, and this is a gas where if you put it in an open container, it's going to pretty much leave the open container. Here, it's a lot less dense than the liquid is. The liquid density and the solid densities, they both are pretty close. So this has low atomic or molecular movement, very low where they don't rearrange, and a high density typically. There are some solids designed like for insulation that have lower densities. Here, there's high atomic or molecular movement. They can move all around and swap places and things like that. And this has a high density, and also is very incompressible. That's a big thing that people think of as the difference between liquids and gases, is that liquids incompressible. By incompressible, I mean they're hard to compress. For a gas, right? Let me make a separation between these. That's solids. For a gas, you have the high, very high atomic movement slash molecular movement, right? You have a low density compared to the others. The other two, they're all very spread out, and this is compressible, easily compressible. You can compress a gas very easily. We pressurize gases all the time, cans of air for blowing off your keyboard and your electronics, or a compressed can of CO2 for paintballing or anything like that, or pumping up a super soaker with air so that it compresses the air inside it, and then you can shoot the water out. If you've ever done that, you notice the water doesn't seem to compress, it stays about the same. That's the liquid, but you keep pumping air inside, so it's the air that you can't see that's actually being compressed in there and making that pressurized vessel. In reality, these three states don't do it justice. There's actually a lot more states of matter, including just solid ice. If we freeze ice, there's actually a bunch of different crystal structures that can form for ice, and each one of those crystal structures is actually a different state of matter. And when we talk about phase changes, changes between the states of matter, there are actually phase changes that occur between them. An example of this would just be changing, crystal lattice, a crystal structure. So graphite and diamond are both just carbon, but they have a different crystal structure to them, and it makes them a different state of matter of the same substance of carbon. They're just a different state of carbon. They're called allotropes, two different states of the same thing. And if you try to go from diamond to graphite, you can actually burn diamond. I think you could probably even do this with a lighter. It doesn't take a really super hot flame. You can actually burn diamond into graphite and have it go through a phase change. And when we talk about phase change at the bottom, I'll kind of bring that back up. But it will go through a phase change when you change to those things. So the solid, liquid, and gas, when we say there's only 3, maybe 5, you include plasma and Bose-Einstein condensation, that's actually very limiting. It turns out there's a whole lot more different states of matter. Even just for ice, there's a bunch of different states of ice that ice can get into as it freezes. All right? So just kind of keep that in the back of your mind. Know the 3 states for this class, but there's really a lot more to it than just that simpleness to it. Okay? So now that we're talking about these things, let's define temperature. So this will be another one of these things. I'm going to tell you what you need to know for this class. So temperature, and the way it's defined for this class, and usually the kinetic theory definition of this, the kinetic theory, is average kinetic energy, so average kinetic energy per particle. And so it makes it sound like this is actually a measurement of energy, and it almost is, but it's not quite. So this is what you need to know for this class. Average kinetic energy per particle. If I give the same amount of energy to 2 different substances, one that has more particles than the other, then the one with more particles will have a lower temperature change. So like if I have a box of gas with, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 different particles in it, and I give it, say, 5 joules of energy, and it goes in there, it's going to raise the temperature up, but that 5 joules is going to split between all 15 particles, whereas if I came to another box and I gave it 5 joules of energy put into it, and it only had 3 particles in it, then the 5 joules would split it between the 3 particles, and this would be the delta T here would be greater than the delta T over here. So this will be for the 15, and this is for the 3. For everything else, considered everything else the same, that would be the case. This would have a bigger temperature change because each one of these would get more of that energy. So this is the kinetic energy, average kinetic energy per particle, and for this class, this is sufficient. It will get you through it, and it's what you should think of for this class for what what temperature is. Now, what it really is becomes a lot more complicated, and it actually changes as it goes along. But uh, essentially, you have to include the way that individual particles and things are going to hold that energy. It's something called entropy. And so, if you look at something like a water molecule, water has a very can hold a whole lot of energy without changing temperature. It's because it has a very complicated molecule where you have you have your oxygen and your two hydrogens, right? It makes this kind of triangle shape. Well, if I give it energy, these particles can vibrate here, can vibrate that way, can vibrate this way. It can spin this way. It can spin around that way. It can move translationally. There's a whole bunch of different ways that it can divide that energy up, which reduces how much the actual temperature changes. So if I give it a certain amount of energy to this molecule, the temperature doesn't change much. Or if I look at just a single particle, like a single hydrogen atom, if I give it energy, all it can do is spin. And spinning this way is the only way it matters, because spinning this way is identical. Spinning this way and spinning this way is different. Even are different from each other, because one's going this way and one's spinning the other way. It's not the same here, so we can only spin and then move translationally over here. So there's only like two ways it can hold that energy. So for the same amount of energy given to this, it'll be a bigger, higher temperature change than given to something like that. It's not a perfect example, but I'm just trying to get you the idea that there are complexities that are involved in here that can affect how much the temperature has changed based on how many places the substance has to store that energy. So this isn't something you really need to know for this class, but just trying to keep it in mind that temperature is not exactly energy, but it is very closely related to it, as in the kinetic energy per particle. So, and notice it's average. The reason it's average is because some of these particles will bounce around as they bounce into each other. You can imagine if this is just a whole bunch of balls bouncing around, they're not all going to have the exact same kinetic energy, the exact same speed. They're going to hit each other, and sometimes some will be going slow and some will be going really fast. But if you average it out, it pretty much stays the same. So this is that microscopic view of it, where some are going really fast and some are going slow. And then we're going to do the macroscopic type of analysis of it. We're going to take the average of the whole thing and call that temperature. So be careful about that too. It's not the kinetic energy per particle, it's the average kinetic energy per particle, because it's different from particle to particle. Okay? Next, we're going to talk about the temperature scales. And so originally we had Fahrenheit, and then we had Celsius, and then another one came along. I'm sure you know enough about Fahrenheit and Celsius. Was the Kelvin scale. And what was noticed was that the way this was done is that if you look at either volume versus temperature, so volume is a function of temperature, or so either volume or pressure as a function of temperature. These things are linear. Volume is linear with temperature, and pressure is linear with temperature. And it was noticed that if you plot out all your points, you got something like this. You had a bunch of different data points all along here. It made this straight line. And I believe Lord Kelvin noticed if you drew this line straight back, it actually eventually came down here and hit the axis. And at this point where it hit the axis, that was the lowest temperature you could have, because at that point you had no more thermal energy going on at all anymore. Everything would be perfectly still. And so he extrapolated back to this point on the graph, and it turned out that in Celsius, this point was negative 273.15 degrees Celsius. And so he took that and said, no, we're going to call this zero. We're going to call it absolute zero. And he's going to say this is the coldest temperature something can be, because at this point there's absolutely no kinetic energy left in any of the particles anymore. And so it came out to be that 0 then Kelvin, not degrees Kelvin, 0 Kelvin is equal to negative 273.15 degrees Celsius. And then the scaling of this stays exactly the same. So to convert between Kelvin, to convert from Kelvin to Celsius, you just add to convert from Celsius to Kelvin, you add 273.15, and to convert from Kelvin to Celsius, you subtract off 273.15. So I could tell you something that's like, if I told you that room temperature was about 300 Kelvin, and I said, what is that in What is that in Celsius? You would just go ahead and subtract that off, and it'd be what, around 27 degrees Celsius, something like that. That doesn't seem right, does it? Yeah. Oh, I'm sorry. It's just I'm sitting here thinking 32 degrees Celsius is freezing, but that's in Fahrenheit. 0 degrees Celsius is freezing, so this is fine. So it'd be about that. You just subtract that off or add it on, depending on which way you're going with it. So that's the idea of absolute zero. It's how you convert it, and we're mostly going to pretty much just use the Kelvin scale. Since this conversion is simply just adding a number on, a change in temperature in Kelvin is equal to a change in temperature in Celsius. So if you're working with an equation or a problem where all you're worried about is change in temperature, you don't have to worry about converting it to Kelvin, because when you take the difference, it's going to be the same for both, because all you really would have done is just added or subtracted 273 from both of the numbers that you were finding the difference between, and it's going to work out to be the same difference. So that's a nice little thing to note, is that it's really easy if you don't have to worry about that. If you're doing change in temperature, you don't have to worry about doing the conversion. There are a lot of things, though, where you need to be in Kelvin, and Celsius is just not going to cut it for a lot of the stuff we do. So get used to using Kelvin if you are not already. Okay, next thing, and I know I'm kind of flying through all this stuff because it's a lot of different things, but none of them are horribly complicated, is internal energy. Internal energy and heat. Okay, so internal energy, this is a pretty simple concept. It's simply the total microscopic kinetic energy and potential energy of a substance. So something like that. Basically, it's all your kinetic and potential energies, all your microscopic ones. So if I'm looking down at particles in a solid, say here, and I have an atom here vibrating back and forth with another atom here vibrating back and forth, well, when they get close to each other, they repel. So at that point, their kinetic energy goes to zero, but their potential energy is pretty high. Then as they repel and vibrate back and forth between each other, they get kinetic energy. So there's a whole lot down microscopically, as all these atoms are all surrounding each other, holding each other in place. There's a whole lot of potential energies calculated between all of them, and kinetic energies as they all bounce and vibrate around like little springs and masses on springs as they vibrate all over the place. And so you have a lot of kinetic energy and potential energy switching back and forth. And so what we look at is the total internal energy. We just look at that, and it's basically just these two things together. It'd be way too difficult to try and figure out what the exact kinetic energy was at a moment, the exact potential energy is. So this is the microscopic view. The internal energy is like the macroscopic view of this microscopic thing. It's like we're averaging it out over both of them. Just in case you're wondering, the variable used for internal energy is actually the capital letter U. Okay, so if you see that somewhere, you'll know what that is. And then the other thing I wanted to throw in this was heat. Heat, as I've mentioned before, heat is work. So heat is work. And remember, work was a transfer of energy. Well, heat is just a transfer of this internal energy, of this thermal energy, because that's what this internal energy is. And so heat is just transferring this internal energy. If I put, these things are all vibrating around, I stick another hunk of metal on here that's, say, they're not vibrating very much, these things aren't moving, then what's going to happen is these are going to start to vibrate and hit the edge of this material and start making these guys move, and you're going to start to get energy transferred between them, and that's what we call as heat. It's just the microscopic version of transfers of kinetic and potential energy between molecules, is this idea of heat. The variable for heat is the capital letter Q. Okay, so heat variable is capital letter Q, internal energy is a capital U. So that's what this heat is. Heat is work, and work is heat. That's essentially what it is. Without heat, we wouldn't be able to do anything, wouldn't be able to do any work or anything like that, and I will come back to talking about heat in just a couple minutes. But first, we need to go ahead and combine this whole idea of internal energy and these different states of matter and heat, and we need to talk about phase changes. So now we're going to actually combine some of these ideas we had. Phase changes. This is whenever one thing changes from one state of matter to another. Changes between states of matter. So this is an ice cube melting into a liquid. This is a liquid evaporating into a gas. This is a gas condensing back into a liquid, like on your cold your icy drink of water or whatever sitting outside the refrigerator, gets all that water on the outside of it. Or this is sticking something in the freezer and freezing it into a solid. It's phase changes. It's what happens going through that. And so what I'm going to do is go ahead and draw a little diagram of what happens basically. So let's say we have this here on the horizontal axis. We're going to have the amount of heat that we add to it. On the vertical axis, we're going to have the temperature, and we're going to start with something that's a solid. And so we start with a solid that's really cold. So this could be like really, really cold water. And what's going to happen is we're going to start adding heat. And as we add heat, the temperature is going to go up. It's not going to necessarily be. I'm trying to make sure this isn't a 45-degree angle. Basically, this is just going to go up linearly, and it's going to go up. And then eventually, what's going to happen is this solid is going to start to melt. So here, solid, it's going to start to melt. And when it starts to melt, something very interesting happens. This graph plateaus. So while it's melting, here it's solid and liquid. It's melting here in this region. So here's solid. Here it's melting. While it's melting, the temperature doesn't change anymore. And then eventually it finishes melting, and the whole thing melts, and then the temperature starts to rise again. And here is when it's just a liquid, right? Just a liquid. And then eventually, after you heat it up enough, something happens again where it plateaus again, and the temperature stops changing, and this is when it's boiling, basically, and you have liquid, right? Liquid and gas at the same time. So it's boiling at this point, producing both, and the temperature stays the same. And then eventually it all boils away, and you keep heating it, and the gas, the pure, just only a gas is left, and its temperature starts to rise again. So I think this part's pretty understandable. You add heat, its temperature rises. This part's pretty understandable. You add heat, the temperature rises. This part's pretty understandable. You add heat, the temperature rises. What's weird is in here in these two sections. Why does it plateau while it's going through a phase change, while it's changing from solid to liquid or liquid to gas? And the same thing would occur too if we did this graph backwards. If we removed heat and started cooling it, it would plateau until it all turned into a liquid, and then temperature would drop, and then it would plateau as we removed heat until it all became a solid, and the temperature would drop. And the answer to this is that during these phase changes, the heat we're adding is not actually going into changing the temperature. All the heat we're adding is going into actually changing the phases of it. Remember we talked before about the difference between the solid, liquids, and gases. So what would be happening, say, as it was going from a solid to a liquid during that phase changes, we'd be breaking the little non-covalent bonds between these things. We'd be making these little molecules break apart from each other and start to move freely. And it's during that time that we're breaking those apart. It's actually called symmetry breaking. That the temperature stops changing while it's going through this phase change and breaking symmetry. Remember I mentioned that there were other types of states of matter like carbon and graphite and diamond. They're just carbon. Well, going from one phase to the other is just symmetry breaking. You're breaking and changing the crystal structure. So that's where that symmetry breaking term comes from. So basically what's happening is you're going through this symmetry breaking, you're going through this phase change, and all the energy is going into actually changing the phase and changing the arrangement of the molecules and the atoms and stuff, and not into actually raising the temperature. So how do we calculate this? Like, how does this graph look for water versus mercury versus hydrogen versus all these different materials? Like, this is obviously going to be a different graph, but how will it be different? How much will it go up during this time? How far over will it plateau? How much will it go up in this time? And we have to introduce a couple of things. Remember we said we were talking about average kinetic energy per particle. And so the things that affect this temperature change is, one, how much of the material you have, right? How much heat you're adding. And then lastly, what the material is. There's a material property that goes to this. And this has to do with that entropy thing I was talking about earlier, where we have to consider more than just average kinetic energy per particle for the temperature. That's really what's going on here, but in order to keep that average kinetic energy per particle definition, a couple of ideas were invented to take care of this. And the first thing is called specific. So specific means per mass, that's always the case. Specific heat capacity. And you might see this without the word specific in front of it. You might just see heat capacity, and sometimes they just call it specific heat. But specific heat capacity is what we're looking at. And the idea is that if we look at the heat capacity, the specific heat capacity of something, it's essentially defined as the heat required to change the heat per unit mass to change the temperature of a subject per Kelvin or per degree Celsius. It's a change, so it doesn't matter if I'm talking Celsius or Kelvin. That's why I was talking about that earlier. The change is the same. So it's the amount of heat you have to add per mass per change in temperature to get it to move. So if we looked at the amount of temperature here, say that was, we looked at how much heat we had to add between here and here and what the temperature change was and what the mass was. So this would be delta T, this would be Q, and then we'd have to look at what the mass was, and we'd do Q divided by this delta T over this M, and we'd get this relationship, okay? And so that helps take care of just heating solids, liquids, or gases. So this heat capacity goes with these sloped parts where it's actually the temperature is rising. Well, what do we do what about during these times where the temperature isn't changing? We can't divide by zero, and so what we come up with is something else called the latent heat. And so there'd be a latent heat of fusion, that'll be between solids and liquids, a latent heat of vaporization between liquids and gases, but ultimately it is L equals heat, the amount of heat required per unit mass to change phases, to go from solid to liquid or liquid to solid or liquid to gas or gas to liquid. It's basically that. It's the heat per unit mass. There's no delta T there anymore because there is no change in temperature. Okay, so that's latent heat and that specific heat capacity. And the way that you're going to see it in this course is they do a little rearranging. I like thinking of it this way because it's like the definition of heat capacity. Heat per unit mass per unit temperature, or per change in temperature, or heat per unit mass to change it 1 degree. But your book and this course gives it to you in this terms where they solve for Q, and it's Cm delta T. And if you like that version better, use it. It's the same function. I just prefer to think of it this way because it's like the definition. And they do the same thing here. They solve for Q, ML. So these are the ones you're going to see, I believe, in your data booklet. These are the ones that are like the definition of them type things, defined as kind of things. And they're the same thing, it's just a rearrangement, personal preference of which way you do it. Even if I was given this, I'd probably solve it for this because this is just the way I think about it and the way my mind works. And I'd use that to solve problems. So how would you go about solving problems for something like this? Well, you could imagine if we had a solid that started at this temperature and we were going to raise it to this temperature, and I asked how much heat would it take to do it. Well, what you're going to do is break this into 3 sections, not always 3 sections, but just in this case 3 sections. You're going to have this part, which is going to be the specific heat of the solid, right? You're going to solve this plus this next little part here. You'll go through and do the latent heat during the blue section. And then you'd have this little part here to do where you go back to doing heat capacity, specific heat capacity, but this time the specific heat capacity of the liquid. So if you were asked, what's the total, the total Q that has to be required to go in there, it would be, it'd be this Q, the green Q for the solid, it would be the blue Q for the latent heat, right? and then it would be plus this Q for the liquid part, right? Liquid part. This was latent heat. This should have been S, solid plus liquid. I probably should have put there instead of just an L for that. And you would look at each of these, and so for this one, you say, oh, Q is C, well, I don't need it. I probably don't need to go to that temperature, the color thing here. I'm just going to go back to gray here. So this is C M delta T, where delta T is this temperature change here, so it'd be the delta T1 plus ML plus C. So this one's for the solid, this one's for the liquid, M delta T2, whatever it happens to be. And of course, if we went going up here, you could go across this and stuff. So however many you have to go through, and that's going to be your total heat you could figure out by doing that. Another version would be if they gave you a temperature change. We took it from here, or I'm sorry, we could say here is what the total temperature is we added. We started at this temperature. Where would it end up? And you'd have to say, well, how much energy would it take to raise the temperature up to the first phase change? And then you'd remove that and say, all right, how much energy do I have left? Can I make it through the phase change? Oh, yes, I can make it through the phase change. And then you look and say, all right, how much do I have left? Can I make it up to what temperature? And you'd go through and kind of solve this in reverse, starting with the total and dividing up. You know, I put this much energy in here. If it stays as a solid, then I'm done. I just calculate delta T. If it's in too much heat that this amount here is is fully covered, then you have to see, does it get me through the phase change? All right, this amount and this amount is totally covered. Then how much heat is left over? Then I apply that much heat to that and see how much the temperature change would be. Okay. The last thing we want to talk about is wasted heat, because we'll start talking about efficiency. Still, again, the amount of energy you put in. We can still talk about this. So wasted heat. We can still do efficiency with this kind of stuff. The amount of heat you put into something versus how much actually goes into doing what you want. Wasted type heats, again, they're coming through types of friction. An example would be a car cylinder. So if we have a cylinder, what happens is you have this cylinder here, this little plunger on it, and you put a little bit of gas in here, you ignite the gas expands, it pushes up and pushes down, and it pushes up this piston here, it moves it up, and that gives you some mechanical energy. And if everything was perfect and worked great, then all the gas molecules, when you ignite them, would fly straight up, and they'd all just be moving like this, and they'd all help to push that cylinder up, and there'd be no wasted heat. But that isn't what happens. What actually happens is a lot of the molecules, they go off in random directions. So some of them go up and hit this, others go off, they hit the wall, right? They hit over here, they hit down here, and when they hit here, they're actually imparting their energy then to the cylinder walls, which don't move, and it doesn't actually do any work for us when they do that. And so what ultimately happens is they hit the wall, they give their energy to the wall, and the car engine then just heats up, and that heat is wasted to the environment. Air blows over the engine, carries that heat away, and it's lost. It's wasted heat, and so you have to look at that kind of stuff. There's always some wasted heat. We can't have 100% efficiency still, and that's the big threat, is this wasted heat where stuff doesn't go, all that energy we give it or the energy we put in doesn't go directly into doing the work we want it to do. It's lost around to the environment. Okay, I think that's pretty much it for this video. Sorry if it was kind of long and I threw a bunch of stuff in there at you real quick, but I thought it was also related. I didn't really want to split it up into different videos, because this stuff was, this stuff at the bottom was reliant on the stuff we learned at the beginning. So I apologize for that. Go back, watch it a couple times till you get it, slow some parts down, think about what I'm saying, and it should be okay. So, all right, that's pretty much it.